Hello and welcome back. Today we're going to be looking at day 13. This is yet another problem where we have a cool array-based solution. So let's get into it. So there's some flavor text. We're operating a claw machine. But basically you get this type of input where we have groups of 3 lines each. They're separated by empty lines. And we have 2 buttons on our machine. Each button will move the crane some amount along the x-axis and some amount along the y-axis. We have a destination where there's some sort of prize, and the question is basically how many times do you have to press each button in order to get to this prize. It costs some amount of tokens to press each button, so it costs 3 tokens to push A and 1 token to press B. There's some language in here about minimizing the amount of button presses. And then the question for part 1 is, okay, so each one of these sections has some total token cost. So you figure out how many times you have to press button A, multiply that by 3 tokens to get the token cost for each press of button A. B costs 1 token, so just how many times are you pressing this? And then you come up with like a total token cost in order to retrieve this prize. Sum up all of your token costs for each one of these groups, and that is your part 1 answer. Part 2, in classic advent of code fashion, says, okay, let's add a really large number. So you're just adding, this is 1E13, and we're adding that to our prize coordinates, and now the question is, okay, how many tokens does it cost to get to the much larger coordinates? And of course your answer is going to be quite a bit larger here. So we're going to be looking at a solution here. There does exist kind of sort of a graph traversal / dynamic programming sort of thing. But the key insight, especially for part 2, where that would be computationally infeasible, the key insight is that this describes a system of linear equations, and we're going to dig into how to solve those. Okay, so I have here, this is a solution from on Reddit. There's a user called Do Pandas Really Exist that I've been talking back and forth with. He has some really cool solutions this year, but this would be an example of the kind of graph traversal sort of way of solving this problem. So he's been using a lot of this kind of like transitive closure idiom, which I've also talked about in previous videos. So maybe I'll link this answer and people can dig into it if you want to look at more of a graph traversal solution to this problem. But anyway, so this is our test input. When I say system of linear equations, we can think about like if we read along the columns here, we have 2 unknown variables, x, well, we'll call it x, which is the number of times that we have to press button A, and y, which is the number of times that we have to press button B. And if you squint, this can kind of be like, 94x plus 22y equals 8400. This is kind of the first column of this answer here. And then the other one would be 34x plus 67y equals 5400. And this is a system of linear equations with 2 unknowns. And so, if you remember like reduced row echelon form or any of the other various methods for solving systems of linear equations like this, they can be solved that way. So I'll show you how to do that with APL here. Alrighty, as usual, we'll start by processing our inputs. So we're doing, what day is it? 13 tests at txt1. That gives us this. We want to split on the empty lines So we could do for each length 0 not equals. That gives us a Boolean vector, which we can use to partition this. Oh, that did not seem to work for each. That's because I have this backwards. For each length, like so, right? Okay, and then actually, now that I'm looking at this, we know the kind of interesting. We know the kind of length of each section. So you could maybe do like a you could maybe generate the indices and then like mod 4 maybe. But anyway, there's different ways to parse this. For each one of these, we are basically really only interested in the digits, and these plus numbers are a little bit of a red herring. There are no negative numbers here. So we can do that by doing membership quad D, partition right for each one of these cells. I've done this in previous videos. This just checks for membership in the set of digit characters. And for each one of these, we can execute to get the actual numbers. Now I'm gonna shape this. Let's see, how do I want to do this? Let's do for each mix. And that gives us a series of 3-row, 2-column arrays. Let's go ahead and mix it again. So we mix it all into a rank 3 array. The shape of this is 4 3-row, 2-column matrices. Let's assign this to P. Now, each one of these matrices in our input describes a system of linear equations. So we can write a function that runs rank 2 on P. Rank 2 means applying it to each matrix. I'm going to do a train here. Why not? So we could do -1 drop, and that will just give us the kind of upper matrix of each one. Now, when I was describing the system of linear equations here, this is, so we want like 94x plus 22y equals 8400. These are specified along the columns, and we want to work on the rows. So we'll do a transpose here in order to get the matrix into the right form. And in order to actually solve the system of linear equations, we're going to be using matrix inverse again. Well, domino anyway. Yeah, domino is certainly a good tool to keep in your back pockets. The last video that I had, I showed how to solve a graph traversal problem with matrix inverse, and now we're going to be using matrix divide. Matrix divide, by the way, is defined here on the APL wiki, and it's basically just taking the inverse of the right argument and doing a matrix multiplication or vector matrix multiplication in our case against the left arguments. And so we want to apply this, J plus apparently. I use domino so infrequently that I don't remember the key combination, but it's awesome when you get to use it. And then we're going to apply that against the last row of each matrix. Okay, so that gives us this now. If we look at the shape of this and we look at the shape of our input, we can basically see that so each 3-row, 2-column matrix has now been reduced to a two-element vector. Some of these are integers. Some of them are fractional. I think if we look at the problem description, there's something in here about for the second and fourth claw machines, there is no combination of A and B presses that will ever win a prize. So we can't like partially push the button. So we're only interested in integers here. We can kind of, if we do, how do we do this? Would it be like, sorry, let me look at, I had a clever way I had a clever way to do this when I was golfing last night, and I don't remember it offhand. Oh, yeah, that's right. I start another train. Okay, so we're going to start another train here, and we are going to floor our matrix here, right? So this is basically turning all of them into integers, and we can see which ones are equal to, we can just see which ones are equal to the original input. So this is flooring them, turning them into integers, and then we get a Boolean matrix that says which ones are integers, and we can then multiply this by our sort of resulting solutions here. So because the solution is found by adding up all of the token costs, um, multiplying by 0 basically means that these elements won't show up in our solution, right? Because adding by 0 doesn't change anything. And then we want to get the token costs for each one, and the left column is sort of the left column is button A, which costs 3 tokens to push, and the right column is button B, which costs 1 token to push. And so we can just multiply by 3, 1 here, and we get this. If we want to get fancy, we can do plus dot times here. This would be vector multiplication. This just adds the 2 vectors together and then sums it so that we get a single answer. And we can see that, so for our first group, we have a token cost of 280. The second group is, there's no whole number of button presses that will get us to the coordinates, so it's 0, and then we have 200. And if we look at our test input, yeah, the first one costs 280. Second and fourth have no solution, so they show up as 0 in our result there. And then for the third one, it would cost a total of 200 tokens. If we add them all up, we get 480. So let's see. Let's call this like F, and this will operate rank 2. And now if we just run that on our input, we get this, and we can just add them all up to get our part 1 answer. For part 2, we are adding 1 E13 to each of the costs here. So, or the prize coordinates. So we can do 1 E13. We can shape that twice so we get a vector of it. We can form it into a column, and then we can prepend 0 twice to get a matrix. If we transpose it, we can then do rank 2 addition on our inputs. And then this will just be running F again to get the total costs. I have to turn on the formatting so that we actually get the larger numbers here, right? And then adding them all together will give us this number. And that's it. I mean, because we're not doing any graph traversal or anything, it makes it like adding these large numbers, it doesn't really matter. We're not doing like an iterative algorithm or anything. Oddly enough, for part 2, I don't think that they actually give you an answer for the test input. So we will simply have to run it on the real input to see if it works. So let's copy this, paste it. We get 29023 and some very large number for part 2. 29023, 967 beginning, 634 ending, which does appear to work here. This formulation that I have over here, by the way, is a little bit golfed. And this, like, ideally you want to keep your data as flat as possible and avoid using these kind of nested arrays. But, you know, sometimes doing the nested approach, like, saves you a character or two, because of the way that the rank operator, you kind of have to put that separator in. So there's different ways of doing it, but yeah, I mean, in general, just try and keep your data as flat as possible and don't do this nested thing. In this case, like um, uh, there's like 320 groups or like systems of equations that we're solving. Um, and so the performance hit isn't that bad for doing this kind of nested thing. But cool. Yeah, that is day 13. This is yet another example of like how you can use the kind of linear algebra tools that are built into APL to get concise solutions. Um, and yeah, I mean it's a quick one today. Thanks for sticking around. Hope you enjoyed watching, and more to come.